It's time to put everything together in our series AC circuit. So we have an AC waveform that we're applying to our circuit that has a resistor, an inductor, and a capacitor. So what we want to do is find our total impedance of our circuit. That'll allow us to find our current and our voltage drops across each of the elements, just like we would do if we were talking about DC. All right, so first thing we want to do is to find our phasor source current. Okay, so find our phasor source current. So this is our sinusoidal equation, and that gives us the peak voltage. We want to find the phasor voltage, which is actually the RMS. So the RMS voltage would be 0.707 times the peak, and the peak is 70.7 volts. So the RMS voltage is 50 volts. Okay, and then we have no phase shift. So theta V is 0 degrees. So that means the phasor voltage is 50 volts at 0 degrees. So when we talk about phasors, we're just talking about the current and the voltage in that polar form representation of a complex number. So next we need to find our total impedance. Okay, remember Z is impedance. Okay, so I'm going to look for our individual impedances first. So the impedance of the resistor is always the resistor value at 0 degrees. So my resistor is 3 ohms at 0 degrees. And in rectangular form, so I'm going to look at this in two forms. We've got our polar form here, and we're going to also find the rectangular form here. So in rectangular form, if we convert 3 at 0 degrees, we would get 3 plus 0J. The impedance of our inductor is always the reactance of the inductor at 90 degrees. So if we had henries here, if our units were henries, we would have to calculate the reactance first. However, in this case, we're given the reactance. We know that two ways. One, they've labeled it X, which we know is reactance. The other way we know is that the units are ohms. Okay, and that's what we need here. So that means we would have 7 at an angle of 90 degrees, or in rectangular form, that is 0 plus 7J. All right, so let's move on to our capacitor, which would be X sub C at negative 90 degrees. And so we have our 3 ohms of capacitive reactance at negative 90 degrees. And in rectangular form, that would be 0 minus 3 times J. So when we look for ZT, we could plug our polar form into our calculator and sum, but it's actually a little easier if you just want to sum the rectangular form, because the real part of our total would be 3 plus 0 plus 0, or 3. And the imaginary part of our total would be 0 plus 7J minus 3J. So that gives us a net of plus 4J. If we convert that to polar form, that's 5 at an angle of 53.13 degrees. And now we're ready to use this information to find our source current. So far we have found our phasor voltage, our ZT, and the reason we do that is so that we can find our source current I sub S, because I sub S is going to equal E divided by that total impedance. So we've got our 50 volts at 0 degrees. Now, it might be easier for you to plug into your calculator the 3 plus 4J. And if you prefer to do that, that's fine. There's nothing wrong with doing that. Just make sure you're putting these parentheses in the denominator, or you'll get a wrong answer. You could also use the polar form. Either is fine. And I'm going to have this return the polar form for me, 10 at negative 53.13 degrees. And I tell you what, I will write down the rectangular form for you if you need this. So that's about 6 minus 8j. Okay, so either is fine. Whichever one you want to use there is fine. Now, this finding I sub s will allow us to find our voltage drops. Remember, in series, the current is the same through each of the elements. So I sub s equals the current through the resistor, equals the current through the inductor, and equals the current through the capacitor. So if I'm looking for my voltage drops, my VR would be that source current times the impedance of that resistor. So if I take the 6 minus 8j and I multiply by the impedance of my resistor, which is simply 3, which would be 18 minus 24j, or in polar form, 30 at an angle of negative 53.13 degrees. VL would equal that same source current times the impedance of our inductor, or 6 minus 8j times 7j. Which is 56 plus 42j. Remember, if you're multiplying j times j, j squared, or I squared, is -1. That's kind of where that comes from. So just keep that in mind if you're doing the multiplication by hand. But that would, in polar form, that would be 70 at 36.87 degrees. And then VC is I sub s times ZC, which would be that 6 minus 8j times -3 times j. Or -24 minus 18 times j. And in polar form, that is 30 at -143.13 degrees. Now, if you want to check, remember that E should equal VR plus VL plus VC, if this is like it was in our DC circuit analysis. If you wanted to add, you could add all of these in rectangular form and see what you get. So for the real part, we've got 18 plus 56 minus 24, which is 50. And then for the imaginary part, we've got -24 plus 42 minus 18, which is 0, which is 50 at 0 degrees. So that actually does work out right. Sometimes in the polar form, it's pretty hard to see that that adds up to the 50 at 0 degrees, and it might be a little easier if you're looking at this in the rectangular form. Some students really like to keep things in rectangular form because it's much easier on the TI 8384 calculator to do that, but I'll let you decide what you want to do. So let's work through another very similar problem here. This is a very similar problem, actually. So I'm going to start with finding our phasor voltage. Okay, so we need the RMS voltage, which would be 0.707 times the peak, which we see is 6. So we have 4.24 volts RMS there. So my phasor voltage is 4.24 volts, but we also have a 60-degree phase shift, so I have to include that here as my phasor voltage information. Okay, part 2, we want to find our total impedance, so we're going to have to find the impedance of each of our elements one by one. So the impedance of my resistor is 1.8K. I'm going to go ahead and write it as 1800 at 0 degrees, or 1800 plus 0J. The impedance of the inductor is 2000 at 90 degrees, or 0 plus 2000J. And the impedance of my capacitor is 600 at negative 90 degrees, or 0 minus 600J. So to find ZT, I could plug in the polar form number, or I could just do the sum in rectangular form, which would be 1800 plus 1400J. And that means ZT would be 2.28 kiloohms at 37.87 degrees. If I'm using the polar form, you can use either form that you want to use. We do that so that we can find our source current, I sub S. Remember, I sub S is the phasor voltage divided by the total impedance. So if I'm using 4.24 at 60 degrees, I can use either the rectangular or the polar form. I'll switch to the polar form this time. 2.28K at 37.87 degrees. So I sub S would be 1.86 milliamps at 22.13 degrees. Or if you want that in rectangular form, that's 1.73, 1.73 milli plus 0.7 milli times J. Again, you can use either form that you want to here. And then if we want to find our voltage drops, VR would be that I sub S times ZR, 1.86 milliamps at 22.13 degrees, times ZR, which is 1800 at 0 degrees, so 3.35 at 22.13 degrees. And I'm going to leave these in polar form, so if you want to practice doing your conversion, go right ahead and do that. Actually, let me leave a little space as we get down to VL. I'll leave a little space and show you why. So I sub S times ZL, the same current because we're in series. This time ZL was the 2000 at 90 degrees, which means we have 3.72 volts at 112.13 degrees. And then skip a little bit, and then V sub C is the source current times ZC. Which is 600 at negative 90. So there we're going to have 1.12 at an angle of negative 67.87 degrees. Now, the reason I left a little bit of a space here is I want to go ahead and write our sinusoidal equation. So we can take our phasor and convert it back to a sinusoidal equation. Because remember, this is our RMS, and this is our phase shift. So what we'll do is first find our peak voltage here. So we're going to take our RMS and divide by 0.707. So here we had 3.35 divided by 0.707. So that gives us 4.74. And that's peak. Okay, so VR as a function of time would be 4.74 sine, 314t. I'm getting that from the original equation up here, 314t, and then plus 22.13 degrees. That came straight from our phasor. And that would be the equation for the voltage that would result from this particular circuit with this applied voltage source. Okay, so the same thing, I can do the same thing for VL. VL peak, whoops. VL peak, let me see if this comes back. Sorry about that. VL peak. Where are we? VL peak. That would be the 3.72 volts divided by 0.707, which gives us about 5.26 volts peak. So VL as a function of time would be the 5.26 sine, same angular frequency, and this time we're using the 112.13 degrees that we found for our phasor voltage there. And then for VC peak is that 1.12 volts that we have here as our RMS divided by 0.707, and that gives us 1.58 volts peak. So VC as a function of time would be 1.58 sine 314t minus 67.87 degrees. Okay, so you won't always have to show the sinusoidal waveform, but it's helpful to understand